That looks great.
Awesome. Sorry about that, everybody. I'm totally new to using notes on a separate screen here. So as I was saying here, before we begin, just a couple of things to keep in mind as we're going through the program. This presentation obviously doesn't cover everything. This subject is huge. It's covered extensively in books about Great Lakes shipping history. It's really great stuff. I love the subject personally. But this is going to be more of an introductory course. So try to keep in mind we can't cover absolutely everything, but it's great if you're really interested in the subject. We will be having learning checkpoints throughout, which means we like some interaction for you guys as the audience. So if you could please use the chat box, and Tricia will let us know what your guys' answers are to all our little checkpoints that happen at the end of each section. This presentation, as you heard, is recorded. So if you miss anything, you can go to the USACE Detroit District YouTube page to watch it in the future if you missed anything. And then throughout the presentation, if you could please type questions into the chat throughout, and we'll try to address them the best we can at the end of each section. We won't necessarily be able to answer every question, especially if there are a lot, but we'll do our best to answer them at the end of each section and at the very end of the presentation. So to start off with, this isn't anything that you guys need to answer or interact with. You can if you want, but have you ever seen a classic car, like in a car show? And just to try and get the ideas going here, kind of think of a classic car and compare it to like a current vehicle that you drive now. Now, I'm sure there's a lot of differences, and kind of think about why those cars are different. What's different? What's different with technology? How is the shape designed differently? And that's basically what we're going to be talking about. Using a modern ship, we'll be comparing how the different parts of the ship have changed over time and why we have those ships today. And so the way we're going to be, like I said, going through the presentation is we're going to be using a modern ship example, the James R. Barker specifically. Kasey and I were very lucky to have a tour of that ship back in November of 2019. And we'll basically be just taking you throughout the vessel and 5 different parts of it and showing you how those different parts of the ship came to be. So first, what we're going to be talking about, which we'll be giving over to Kasey in a second here, is a ship length, why ships are as big as they are on the Great Lakes and why the sizes differ a bit on both sides, US and Canadian. Hull design, which would be things about the cargo hold, everything kind of where the cargo sits and how the crew get throughout the vessel. And then we will be talking about the self-unloading system, which is that big scaffolding part of the vessel in the picture that you see there, kind of shooting off to the side, how that came to be. The engine room, how propulsion on Great Lakes vessels has changed over time. And then finally, the last section we'll be talking about is the bow and stern design. So that will be everything from the different pilot house versions, just kind of comparing the two, the classic and the modern Great Lakes ship design. So to start the tour of the ship here, of the James R. Barker, I'll turn this over to Kasey at this time for her discussion of how ship length has changed over time.
I just sent it over Kasey's way.
Correctly?
We can hear you, Kasey.
Okay. So to start off today's program, we're going to start by talking about ship length and how the Great Lakes environment has affected ship size over time. The vessel that you see here is the James R.
Kasey, are you able to get closer to your mic? It kind of like, it was good at first and then it kind of got lighter as you started talking. Let's try that again.
Is it better right here?
Perfect, yep.
Okay. So to start today's program, we'll be talking about ship length and how the Great Lakes environment has affected ship size over time. The vessel that you see here is the James R. Barker. She measures 1,004 feet in length, 105 feet in width, and roughly 50-some feet in depth. There's only one obstacle that prevents the Barker from going to the Atlantic Ocean, but for the purpose of this discussion, we'll be talking about two obstacles. First, I want you to imagine that you are a French fur trader in the 1600s. You are exploring new lands in a 36-foot birch bark canoe that was adapted from Native American designs. Native Americans in various tribes have been living in the Great Lakes region for thousands of years and had been using dugout canoes and birch bark canoes wonderfully. So you are paddling up the Niagara River, and all of a sudden you hear a thunderous roar around the next bend. Then you see Niagara Falls. Your group then decides that it's probably time to turn around and find a new route. From the St. Lawrence River, the French fur traders would use the Ottawa River to go to Lake Nipissing and then down the French River into Lake Huron. From here, they would paddle to the St. Mary's River and start going up the St. Mary's River until they hit the St. Mary's Rapids. Here, the canoe would have to be unloaded and carried or portaged around the rapids until they could set it back in the water and load it again. In 1797, the Montreal-based Northwest Company did build a small lock here for the canoes, but that lock was destroyed in the War of 1812. It would be another 43 years that the St. Mary's Rapids would be an obstacle to shipping traffic. Back around Niagara Falls, momentum was building behind William Hampton Merritt's idea to construct a canal connecting Lakes Ontario and Erie. Niagara Falls presented a problem for mariners trying to reach Lake Erie from Lake Ontario or vice versa. William Merritt's idea to use the Welland River was gaining popularity and financial support though. Then the first Welland Canal was opened in 1829. This first canal featured 40 wooden locks that were each about 110 feet long. So what did this mean for any vessels trying to use those locks? Well, any vessels wanting to go through there would have to be 110 feet or less to be able to use the locks. At this time, wooden sailing vessels had been common on the lower lakes for about a century, but now the vessels from Lake Ontario could also access Lakes Erie, Michigan, and Huron. Ship sizes then increased with trade and industry, and the wooden locks became a bit too small for the larger vessels. The second Welland Canal was completed in 1853. This canal that you see on the left featured 27 stone locks, each measuring about 150 feet long and 27 feet wide. Small sailing vessels, like that of the 88-foot-long Osceola, would comfortably fit through these locks. However, vessel sizes kept growing. Steel hulls also made an appearance on the Great Lakes, and then they soon took dominance as the preferred building material. Wooden hulled vessels had a limit on size due to the height of the trees in their area. Steel, however, could be produced to any length or specification, and so its popularity just skyrocketed. Because ships were also getting bigger, there had to be another canal system built. The third Welland Canal was completed in 1887, and this canal was almost double in length and nearly double in width than the previous canal. Vessels like the 245-foot Algonquin built in 1888, were designed to go through canals like this perfectly. Today's Welland Canal was built between 1913 and 1932. The canal system now features 8 locks instead of 20 or 40. And what does this mean for vessels today? Well, these locks, especially 4, 5, and 6, have to be pretty short. They're actually only about 740 feet long. So any vessels that want to use today's Welland Canal has to be 740 feet or less to get from Lake Ontario to Lake Erie or vice versa. Back to Lake Superior. In the mid-1800s, copper and iron ore were discovered around Lake Superior. And so to provide easy access to the resources around Lake Superior, the state of Michigan built 2 locks at the St. Mary's River in 1855. And these became known as the Old State Lock that you see on the left. And these locks were 350 feet wide, 350 feet long and 70 feet wide. Multiple small vessels could fit through these locks at one time to get into Lake Superior. Vessels similar to the Osceola. With an increase in shipping traffic and due to ship sizes still increasing due to steel hulls and their operational environment, these locks would have to be replaced, but the state of Michigan did not have the funding at this time to maintain these locks or build bigger ones. So in the 1870s, the state of Michigan passed legislation to turn the locks over to the federal government, which is where we come in. Congress almost immediately began designating funds to build the new lock, and the new lock was completed in 1881. This was the Witzel lock. This one measured 515 feet in length and 80 feet in width. Vessels like the schooner barge Iron Queen would go through here quite wonderfully. As time went on and traffic frequency increased and vessel size also increased, we needed another lock. The Corps of Engineers responded by building the first Poe lock. This one that you see on the right was built in 1896 and measured 800 feet in length and 100 feet in width. And you can see in these pictures that the Poe lock could fit multiple vessels at the same time. But as vessels got bigger, they started to push that 800-foot capacity of the Poe lock. So next we had the Davis and Sabin locks to keep up with vessel traffic. The Davis and Sabin locks were built in 1914 and 1919, and they are twin locks. They both measure 1,350 feet in length and 80 feet in width. And the picture of this vessel here is the 580-foot long James A. Farrell, built in 1913. These 2 locks, the Davis and Sabin, are so large that 2 of the Farrells would fit in one of those locks at the same time. In the 1920s and 30s, shipping companies then asked for a new, deeper lock. The project then received a boost during World War II when the supply of iron ore became a matter of national security. The project was approved, and in 1943, the 800-foot long and 80-foot wide MacArthur lock was finished. To further accommodate the needs of vessels and companies, and because vessel sizes were still increasing, the second Poe lock was built in 1968. In less than 4 years, the first 1,000-foot vessel would go through the Poe lock. And these MacArthur and Poe locks are the 2 locks used by commercial vessels today. So if everybody wants to get their chat functions ready, we have the first learning check. So my question to you is, what are the names of the 2 obstructions and man-made features that guide ship length?
Can you repeat it again, Casey?
What are the 2 obstructions and man-made features that guide ship length? I'm seeing a lot of great answers. Yes. So we have the Niagara Falls at the Niagara River, and to bypass that, we have the Welland Canal. And then the obstruction on the St. Mary's River was the St. Mary's Rapids, and the Soo Locks were built to get around those. Okay. And Tricia, did you want me to just continue forward into the next topic?
Sure, that's up to you.
Okay. We'll go ahead and get started with hull design. So first we'll talk about hatches and hatch covers. The vessel that you see to the right is the Lucia A. Simpson, built in 1875, and we'll reference it several times in this section. And then on the left, we have a graphic of basically what a cross-section of a modern freighter looks like. So hatches are spaces on top of the deck that open into the cargo holds below. The hatch covers are like the lids to these hatches, the same way that a cookie jar has a lid to it. So on the Lucia A. Simpson is an example of a classic lake schooner with 3 masts. She measured 127 feet long and 28 feet wide. And she had 4 hatches that we see here, relatively small ones. And her hatch covers were made of wood with a canvas tarp covering them to keep water out. And then we also have a picture of her deck and 3 hatches visible on deck. Here we have the 342-foot long Montezuma, built in 1903. Here we see how a larger wooden sailing vessel now has more hatches, and these hatches are also bigger. These 9 hatches measure 12 feet long and 7 feet wide. I'm going to fast forward to some of the steel vessels. The first single sheet steel hatch covers used on the Great Lakes were by whalebacks like the Thomas Wilson. Steel hatch covers provided a seal better than the wooden hatch covers with the canvas tarps. And then the popularity of the steel hatch covers soared. Today, on modern vessels, we have huge steel hatch covers, like on the James R. Barker. The Barker has 36 hatches on her deck, which open into 7 cargo holds located below deck. And each hatch covering measures 65 by 11 feet, and they weigh roughly 6 tons each. So you might be wondering how they get them off. Mounted above deck is a crane, and that crane will do all the heavy lifting of those hatches. Now for the function of a vessel. We'll talk about the cargo hold. So here we have a cross section of the Lucia A. Simpson on the right. The Simpson did not have any hogbacks in her cargo hold, and her cargoes basically would have been loaded and unloaded by hand with shovels, buckets, and wheelbarrows. Today's modern freighters, we do not have to do that. Here we have the inside of the James R. Barker and the Mesabi Minor. They're sister vessels, and these feature what we call hogbacks in the bottom of the cargo hold. These hogbacks work basically as funnels to direct all of the cargo to the trap doors that lead to the self-unloading system that Scott will be talking about momentarily. The cargo holds pictured here are approximately 4 to 5 stories deep. Next, we'll cover ballast tanks. Ballast simply means counterweight for the purpose of this discussion. Old wooden sailing vessels used to use sandbags, rocks, and coal as ballast in their holds. So if they were traveling anywhere empty, they wouldn't be riding too high in the water. Because over time, easy access to these materials faded, the idea of having vessels with their own special compartments for ballast started to grow in popularity. So the system that we have today, when a vessel is in port and we'll say it's discharging limestone, it will be loading ballast water. So as the cargo disappears, you have that same weight in water going onto the ship to keep it balanced. And then in the second part, when the cargo hold is empty, the vessel will have quite a bit of ballast water, again, to keep it ballast in voyage. When we get to the next destination and we start loading cargo again, the ship will start to discharge the ballast water to get rid of that weight to make room for the weight of the cargo. And we can see in the fourth part of this graphic, when the cargo hold is full, the vessel will have absolute minimal ballast water with it. So next we'll talk about tunnels. Yes, boats have tunnels. These tunnels are long accesses that were designed in ships to provide safe passage for crew members from one end of the ship to another. Storms, blizzards, and freezing temperatures have plagued Great Lakes mariners since the shipping industry began. And once steel hulls could support the weight of this innovation, tunnels became integrated into Lakes freighter design. The photo on the right here is from the William A. Irvin. She was built in 1938, and she features the first tunnels on a Great Lakes freighter. And you can see how these tunnels do very much resemble an old Navy vessel. At least that's what they remind me of. So next, we have a tunnel from the James R. Barker. And they've changed quite a bit. The part of the ship that we are in is below and to the side of the cargo hold, but above the lowest ballast tank and hull of the vessel. Now, as you can see, these tunnels have changed quite a bit to be a little bit nicer and safer. However, tunnels these days aren't used necessarily as much for shelter and safe passageway from storms, but rather as access points to machinery like conveyor belts and other equipment. So looking at the two cross sections of these hulls, they're kind of like two halves of different sub-sandwiches. What similarities and differences do you see? One of the biggest changes is the hull material. We've gone from wooden sailing vessels to steel-hulled vessels. Modern vessels now have these large hatches and hatch cranes, whereas the older vessels had very small hatches that you could lift off by hand. Old vessels did not have tunnels or special ballast areas, whereas today's modern vessels do. And one more note about the hull. Today's modern steel-hulled vessels, that hull is only about 1/4 to 1/2 inch thick steel. It doesn't sound like much, but they're very strong. The only thing that they have to watch out for is ice in winter. If everybody wants to get your chats ready, we're going to go to the next learning check. And if you could, you can try to identify all of them or just one or two of them with the word bank at the top. So we've got A and B, hatch and hatch covers, cargo hold and hog backs. So say C is ballast tanks, D is where we have the tunnels, and E is the outside hull of the vessel. Okay, and this is where I will turn it back over to Ranger Scott.
All right, thank you, Casey. So for the next part of the presentation here, I'll be taking you to look at the self-unloader on the James R. Barker and where that came from. The Barker has a 250-foot self-unloading boom, which you can see in the picture there. The boom is at the very end of the self-unloading system, so it doesn't actually, it's at the very end. There's a whole lot to the system that you can't actually see. The boom can be aimed at on either side of the vessel for unloading, so they can aim where they're going to unload the cargo specifically. Via a huge system of conveyor belts that go throughout the vessel, the Barker can unload 10,000 tons per hour of its total 63,300 ton capacity at full speed. In theory, the whole vessel could be unloaded in about 7 hours time, but it's more realistic to unload in about half a day's time or more, depending on the cargo that they're carrying and the potential for breakdowns, which can happen with these huge conveyor belt systems that go throughout the ship. And again, that's where the self-unloading system is located. So how does the self-unloader work? Well, The cargo from the cargo hold first drops onto a conveyor belt through a system of funnels, which Kasey told us is the hogbacks that you can see in the cargo hold, is then taken towards the back of the vessel by those conveyor belts. There the cargo is trapped between conveyor belts and taken up like an elevator up to the boom, which I've already showed you, where the cargo is ultimately unloaded into a hopper or onto a dock. So self-unloading technology has only been around for about 100 years, but what did they do before they had self-unloading systems? Well, it was hard work. Throughout most of the 19th century, the 1800s, the unloading of vessels was done by hand and shovel, so it could take days or even a week or more depending on the size of a ship. This meant that vessels couldn't make many trips during a single shipping season, so only a few. By the 1860s, steam-powered cranes were being used to speed up the process, which you can see here in this photo from two harbors of coal being unloaded from a lake schooner in the 1880s. And you can see those cranes here in the buckets for lowering into the holds here so that they can be unloaded. This shore-based unloading technique would be improved upon through the years with larger and larger machines. In 1898, the HULETT ore unloaders were invented to unload Great Lakes ships more efficiently. These gigantic pieces of machinery could unload a standard 600-foot freighter in half a day's time or less, taking 17 tons of cargo out of the hold per scoop. That's how much this single scoop can actually take out of a vessel at a time. Usually they had 2 or 3 or even 4 lined up in a row so that several could work on one ship at a time. The time saved allowed vessels to complete more trips during the year, which made more money for their owners. At their peak use, 77 HULETTs could be found operating across the lower lakes, mostly Lakes Michigan and Erie. The last operational HULETT machines unloaded their last Great Lakes freighter in 1992, so not too long ago, due to the wide use of self-unloading systems. And here we have the introduction of the self-unloading system on the Great Lakes. In the late 1890s, the Lakeshore Stone Company acquired a limestone quarry on the western shore of Lake Michigan near Milwaukee, and they hired engineer Towner Webster to design a revolutionary crushing plant. The company, in order to transport the limestone that they would be quarrying, they bought an older wooden freighter depicted here known as the HENNEPIN. In order to make unloading faster, Webster designed the conveyor belt system we use today depicted above, making her the first self-unloader on the Great Lakes. So you can actually see here again, here's that conveyor belt system in the hold and what then would be considered a hogback. And then you can see the self-unloading boom here on deck where they can aim it off to the side. Besides saving time, the self-unloading system also allowed the HENNEPIN to unload cargo without the need of shore-based equipment. So they could practically unload cargo on any dock that they wanted to. They weren't necessarily restricted to specific areas where they had to unload with the shore-based machinery. Modern Great Lakes self-unloading systems came, as I said, from this basic design. If you're curious, that's what limestone looks like, and that was what the system was originally designed to carry. Limestone is still a major cargo here on the Great Lakes because it has so many uses. Although self-unloading systems were more efficient, it took several decades before they were standard for Great Lakes ships. It was believed by ship owners and shipbuilders that self-unloading technology couldn't unload the natural iron ore depicted above here. Self-unloaders were mostly used to transport limestone and coal early on. Once taconite pellets began to dominate the industry in the 1950s and 1960s, it was discovered that self-unloaders could carry and unload the cargo efficiently. In the 1980s, it was almost crucial to have self-unloading systems on board ships to keep them more competitive. Any older ships that lacked those self-unloading systems would eventually be scrapped or retired because they weren't able to make money as efficiently. Today, all operational American ships on the Great Lakes, like the James R. Barker, have self-unloading systems. So again, if you'd like to participate here in the chat function, we have our first learning check. So this is what we'll see if you guys know. Which of these freighters that you can see have self-unloading systems from what you know, what we just talked about? I'll give you a minute or two. A, B, or C? Which freighters have self-unloading systems as far as you can tell? So the answer is that freighters A and C have self-unloading systems. You can tell by, again, that kind of crane or scaffolding structure that's usually towards the back of the vessel. Some ships do have it up front these days. It's actually a more modern design, but we'll be talking about that at the very end a little bit. And then one more quick question, if you can answer in the chat. What are the advantages of self-unloading system over shore-based systems like the huge HULETT or unloaders? Is it A, they're generally faster, B, allows boats to unload at any port, C, natural iron ore could be unloaded quicker than taconite pellets, or D, answers A and B? Which one do you think? I'll give you a minute or two. And so the answer is D, A and B. So self-unloading systems are generally quicker than shore-based systems, and they allow the ships to unload at any port or any dock that they would like. They're not restricted to one particular port because they have to use cranes that are located there. And just as a quick pause here, does anyone have any questions as of right now on anything we've covered so far? And Tricia, if you could let me know if there's any questions, I'll give you a minute or two.
Absolutely. There's one inquiry that says, please report the name of the designer of the HENNEPIN's unloading system when you can, if you know.
Yeah, yeah, it was, let's back up real quick. It was Towner Webster, I believe was his name. For the Lakeshore Stone Company, he's the one who designed, one of the ones who designed the system. I'll go back to where I was at here. Any other questions, Tricia, before I keep going?
Yes, there's one more question. How did the sailing vessels get up to the Detroit River and St. Mary's against the current?
Yes. So in most instances, especially with the Detroit River, as far as I know, they were actually pulled by tugs. There was a huge fleet of steam tugs that were stationed throughout the Detroit River to help tow those schooners between the lakes. And I believe that was probably the same with the St. Mary's River, but I'm not quite sure on that end. And eventually later on too, the consort system, which involved steamships, would actually pull an extra schooner sailing vessel or barge behind them. So they got through the rivers that way as well.
There are two more questions if you feel you have time.
Yep, let's do one more. And then we'll keep going.
Yeah, we can always answer these at the end, folks. This one is, how is the flow of the cargo meteored onto the belt system? Once it is opened, can it be closed again before the cargo is empty above it?
Yeah, so I'm not going to back up through the PowerPoint like I did just a little earlier, but there was a picture in there that showed that there are, with those hogbacks, there are several little openings that you can control cargo being allowed onto the conveyor belt or not. Basically at small hatches that crew members would go to the bottom of the ship in those tunnels that Casey showed, they would release the cargo down onto the conveyor belt. So I believe that answers the question there. All right, continuing on. The next part of the vessel, as you can see, I'll be taking you through is the engine room. Here in the picture on the left, you can see the Barker's, one of the James R. Barker's massive 8,000 horsepower, 16-cylinder fuel stick diesel engines. And these two of these engines propel the Barker at about a speed of 13 knots tops, which is about 15 miles per hour, give or take. And as you can see from this photo, these engines are just truly massive. They're about a story tall and require a lot of maintenance. There's several crew members that are dedicated just to operating the engine for the vessel. So how has ship propulsion changed over the years, you might ask? Well, first, the earliest form of propulsion on the Great Lakes was human strength and the use of sails, sometimes together and sometimes just on their own. During the fur trade era, Montreal canoes, as depicted on the left there, were the dominant form of commercial transportation on the Great Lakes. Sailing vessels, which were few in number during the fur trade era, began to dominate the lakes by the early 1800s so that cargo could be carried in greater quantities. And private companies were allowed to actually operate. The gaff-rigged three-masted schooner that's shown on the right there was the most popular type of sailing vessel on the lakes for its ability to operate with a smaller crew and its ability to sail against the wind. These vessels were more popular than the classic square-rigged vessels, kind of like what you see on Pirates of the Caribbean, those types of ships. Although those ships were faster, they required more crew members. So the lake schooner depicted here became the dominant sailing vessel by the mid to late 1800s. And then the introduction of steam, which was a huge improvement for vessels on the Great Lakes. Invented in the 1700s, the first steam-powered vessels on the Great Lakes were built in 1817 on both sides of Lake Ontario, or actually entered service, excuse me. Both the Canadians and the Americans built steam vessels at about the same time. The vessel you see here is the first American steamship vessel, the Ontario. These early steam vessels had paddle wheels amidships, meaning midway between the bow and the stern, which you can see here. And that's how they were propelled, by being connected to a steam engine. You can see this in a little bit more detail on the photo on the right. These vessels had sails as well, which were used with or without the steam engine in windy conditions. So sails were actually used on steamboats for quite a long time as kind of a secondary way of keeping a vessel going. But early on, the steam engine might not have really been used unless it wasn't windy, so they would use it more often. Steamboats, because of how reliable and faster they were, they quickly took over the business of transporting passengers and package freight early on because of their reliability and timeliness. Sailing vessels like the lake schooners mentioned in the previous slide became dedicated to transporting bulk cargoes like grain and iron ore, since they were much slower and it didn't really matter on the timing of when those were delivered. And then we go from the side wheel system to the propeller. Here we have the revolutionary Great Lakes vessel Vandalia. She was the first Great Lakes vessel built with a propeller rather than the side wheel system. Still powered by a steam engine, the propeller sat below the water at the stern, which you can see here. The propeller system was adopted so that steam-powered vessels could actually fit through the Welland Canal system. The problem with side wheel steamers was that they were too wide because of the paddle wheels on each side, but the propeller didn't add to the width of the vessels. It just sat in the back at the stern underneath the water. Although boats with propeller systems were slower than side wheel steamers, they were more efficient and used far less fuel, which was wood at the time. Because the engine was moved to the back, this made steamboats lean backwards, forcing the use of arches to keep these boats stable in stormy conditions, which you can see here. Here are two examples of those arches in use. on a package freight slash passenger vessel here on the left, and you can still see those arches used in the hull of one of the early steam bulk freighters in the 1860s. So it was a common design. It was also used because wooden ships, as they got longer, they needed something to keep them stable and not bending a lot in wavy conditions, along with the weight of the engine here at the back for the propeller systems. And then next came the triple expansion steam engine. Early on, steam engines used on the Great Lakes only had 1 or 2 cylinders, so they weren't very powerful. By the 1880s, we had this popular engine that was used in almost every Great Lakes vessel between the late 1800s and the 1940s, around World War II. The triple expansion steam engine depicted here, they were powerful and usually rated between 1 to 2,000 horsepower each. And they were about 2 stories tall, so they were huge. And as you can see here on the left with the Meteor steam engine, this is where the engine crew would work on it, but it actually went below the floor quite a bit. And as you can see from the animation here on the right, high pressure steam entered through the first cylinder here and passed through the other 2 as pressure was lost. But this is how the propeller was turned down here. The last triple expansion steam engines were used in the Great Lakes vessels in the 1980s and 1990s. So it wasn't too long ago that there were still a few ships on the lakes that had these triple expansion steam engines. And then finally, we are on the modern engines that we have here on the Great Lakes. And these 2 systems are still in use today. The steam turbine here on the left, which is on the William A. Irvin. There are only 5 Great Lakes vessels today which still use that system that are operational and used for bulk cargoes. Those are the Wilfred Sykes, the Arthur M. Anderson, the Kasey and J. Callaway, Philip R. Clark, and the Alpina. The diesel-electric engine, like the one from the Mesabi Minor and like the Barkers that we showed at the start of this section, represent the far majority of engines used today on modern Great Lakes vessels. Although both engine types were introduced on larger Great Lakes ships around the same time in the 1920s, as you can see on the bottom, it took many years for the diesel engines to become the majority because fuel was expensive for diesel engines and hard to come by when coal was widely available. Early diesel engines were also not powerful enough to power larger Great Lakes ships, so early on they were actually used on smaller vessels. The steam turbine on the left dominated over the use of the triple expansion engine because less crew members were needed to operate and maintain it. The diesel-electric engine has been the dominant engine type in the last 50 years. So again, these engines technologies changed because as they got more efficient, less crew members were needed to operate them. And then the diesel engine at the right is now the most popular type because it's the easiest, or at least less crew members are needed to operate them. All right, so the next learning check here at the end of my section. If you guys can see, what is the chronological order from what we just talked about? In the word bank, we have the steam side wheel, human strength slash sails, diesel electric, and steam propeller. 1 through 4 here, what is the order that these guys go in chronologically for how engine systems changed over time? And I'll give you a minute or 2 to put in some answers in the chat. What is the oldest all the way up to the modern system? All right, just to keep things moving along, I will show the answers here. The oldest of the 4 depicted is human strength and sails with the Montreal canoes and the sailing vessels. Next, we have the steam side wheel system, which was the earliest use of steam on the Great Lakes. Then we have the steam propeller, which first was introduced in the 1840s. The propeller is still used today, but today we have the diesel-electric engine that operates most of the ships. And so that kind of ends with my section here. I will be turning over the last section of our presentation over to Kasey here in just a moment.
Okay, thank you, Scott. Next, we'll be talking about bow and stern design. Starting in the 1860s, wooden sailing vessel designs started to change from their ocean-going cousins. On the left, we have an example of the classic three-masted lake schooner. This was the favorite sailing vessel of mid-19th century sailors due to their maneuverability in small spaces and stability on open water. This one's name is the Resumption. She was built in 1879. And as Scott somewhat mentioned, the lake schooners had their sails set up a bit differently than ocean-going schooners. Lake schooners generally had some taller masts, and they were, again, just generally larger than the ocean-going counterparts. On the other hand, the picture on the right, we have a scow schooner. This is the Ishpeming, built in 1872. Scow schooners were designed basically like floating rectangular boxes. They would fit through the canals and locks very easily while still trying to maintain as much cargo space as possible. They had vertical hulls and flat bottoms that worked very well in the canal system, but they were deemed too unruly on the open water. Wooden sailing vessels like these had the helm located at the stern with a small cabin for crew quarters as well. The shipbuilder, Eli Peck, seeing how some of these different designs and technologies were affecting the shipping company, decided to put some of them together. He wanted to design a lake freighter that would ply through the water like a pointed lake schooner, yet fit through canals and locks easily like the boxy, shallow hull of a scow schooner. He also added an engine because in passenger and package freight service, like Scott mentioned, they're very reliable. To provide greatest visibility to the captain, the pilot house was located at the very front in the bow of the vessel. But for him to be able to see clearly where he was steering the vessel, they kept these poles, which we also call bowsprits, so that the captain could see where he was going. And these function very much like a hood ornament on a car. The result of Eli Peck's designs was the R.J. Hackett, which was built in 1870. And this is really our first model of the Great Lakes bulk freighter. As we discussed earlier, vessel sizes continued to increase. Steel became a favorite hull material, and several technological advances were made around the turn of the 20th century. So here we have some early classic lakers, the Augustus B. Wolven, built in 1904 on the left, and on the right we have the William A. Irvin, built in 1938. These classic lakers follow the R.J. Hackett's design, having a rear superstructure and engine located in the stern, and then having a pilot house with more accommodations located at the bow. But everything in between was specially designed for the cargo. The classic lake schooner has the pointed bow, the bowsprit, pilot house forward, and again, that engine and more superstructure at the stern. If you fast forward about half a century, we get the Stuart J. Court. This was the first 1,000-footer built in 1972, and you can still see how from the R.J. Hackett's design, she's got that vertical boxy hull, the somewhat pointed bow with a pilot house at the bow, as well as a stern superstructure and engine room. However, the James Barker changed this design. Ocean-going vessels made an appearance on the Great Lakes after World War II, and after seeing their designs, having the pilot house at the stern, all accommodations at the stern, some of the Great Lakes shipbuilders thought that was a pretty good idea. This design provided more cargo space by reducing any empty space at the bow, and it also saves money and material during construction. Also, because of today's technology, captains no longer need to sit way up front at the bow to see and communicate with other vessels. Radar, satellite, and radio have filled many of those needs. The Barker was launched in 1976, and she was the first 1,000-footer to have all accommodations and just everything about the superstructure located in the rear. And then this would be the design for 10 other 1,000-footers. And just to separate those modern and classic a little bit, on the left here we have the stern of the Mesabi Minor, and you can see just how boxy the stern is, and the somewhat rounded bow of the James R. Barker on the left. So these are certainly a bit different from your classic Great Lakes freighter. So we have a few more modern vessels, and these do still follow that more modern design, a rounded bow and crew accommodations and pilot house at the stern. These are Great Lakes freighters, the American Mariner and Great Republic. Although the 1,000-footers can carry the most cargo at one time, there are still places on the Great Lakes that the 1,000-footers cannot get to. So to transport any cargoes to those locations, we still need some of these smaller vessels that can fit into those tight spaces. So you want to get your keyboards ready one more time. I talked about two different kinds of Great Lakes freighters. Can you name them? So here on the left, we have the John G. Munson. She's got a pointed bow, the pilot house at the bow, and more stern superstructure and engine at the stern. And then the James R. Barker with the pilot house and everything at the rear. So the two general types of vessels that we see today are classic and modern Lakers. And so what is the whole point of this presentation? Why are we talking about innovation? Well, right now we have the Interlake Steamship Company, and they're building the Mark W. Barker, which is being built in Sturgeon Bay, Wisconsin. She'll be launched in mid-2022, one more year, and her length, like other freighters, will be limited to traveling up rivers like the Cuyahoga River on Lake Erie. and her hull will be specially designed for efficiency and for carrying salt and other bulk cargoes. The self-unloading system will be placed at the bow rather than in the front of the pilot house for easier access to customer docks. And she'll be equipped with two 16-cylinder EMD diesel engines with the lowest possible environmental impact. Finally, she'll have a rounded bow like other modern Lakers and an aft pilot house. And at this time, I will turn it over to Tricia.
Okay, let me get this up for all y'all. Okay. Before we get into questions, I wanted to update everybody on the status of our visitor centers. Not much has changed. If you've attended our previous programs, we are pretty similar to last time. So the Lake Superior Maritime Visitor Center, we still have cell phone tours outdoors accessible on your mobile device. There's the virtual online tour of the museum. We are still here during business hours answering phone calls, and there's the link to the online gift shop. And for the Sioux Locks Visitor Center, the park is now open, has been open from 9 a.m. to 6 p.m. And we will open our facilities once they can comply with state and federal guidance when local health conditions improve. Both of the visitor centers are preparing for the opening of the vessel season that will be happening fairly soon as well. So this will be updated again the next time you hear from us. For next time, if you were here for the beginning of the program, this is the program that will exist on April 1st. Again, that's Celebrating Winter in the Spring in Northeastern Minnesota region, presented by me. So you can join me again, hopefully in a couple weeks. And here's some links as well to be able to access that recording and our Facebook pages for you to follow. So I'll just jump right into some of the questions that were asked previously that we weren't able to answer. Why did oar companies build their own vessels? Scott and Kasey, take it away.
I think the question, did oar companies build their own vessels? To answer the question there, they did not. Shipyards were usually operated by someone else. So companies would order a vessel per se, which they still do today, and they have a different company or shipyard build it for them, and then they buy the freighter that they had built. And that's what Interlake is doing today. The Sturgeon Bay shipyard, I can't pronounce the name of it, but in the very olden days, in the early 1800s, usually ships were built by individuals and operated by the same people, but that changed pretty quickly with established shipyards that were operated by separate companies.
Excellent, thank you for that. Sorry, I threw in the word why at the beginning, and that's probably why that was confusing.
Yeah, no, I saw it earlier, so I wanted to make sure I answered the question, addressed the question correctly.
Excellent, thank you. Next question is, what was the reason for whaleback design?
Kasey, you could take this one if you know the answer.
Oh, so whalebacks, the designer of those, Alexander McDougall, was a ship captain on the lakes, and he was towing some of those scow schooners and lake schooners behind him, And he just sat there watching them and watched how squirrely they were in any type of inclement weather. So he thought that there's got to be a way to design a vessel that's not going to be this squirrely. And what he came up with was the whalebacks, which basically are kind of like a big cigar that sits most of the way underwater once it's fully loaded. And so during inclement weather, this allowed any storms, any waves or anything just to wash straight over the hull rather than smacking the side of the hull and making the vessel squirrely. So that was the reasoning behind that design. However, the cargo hold and the hatches didn't make them as accessible to unload, especially with unloading shore-based unloading equipment. So that's why the design also kind of fell out of popularity, even though it was efficient and it worked.
Great, thank you. I'm not sure if this was answered for you, Tom, but I'm going to ask it again anyway. What is the diamond-shaped structure above the paddle wheels on early steamers, and what did it do?
Yeah, so I saw the answer, or someone answered it correctly. That was the steam engine. It's called a walking beam engine. I wish I had my slide up to show, but it only had one piston, and it basically looked really similar to the early steam engines that were used in mining shafts. But that's basically what it was. And whoever answered that, thank you. That is the correct answer.
Awesome, thank you. Another one is, do you know if the 1,000-footer bows are round, elliptical, or parabolic in general shape?
Do you know, Scott?
I'm not super familiar with the differences between those terms. From what I've seen from above, the bow looks actually kind of rounded, but still boxy, and it's kind of hard to explain. So maybe that's the reason why Tom asked that. I don't know if you have an opinion on that, Casey, but that's what I can tell from above anyway.
I have a really good picture from the bow of the Barker that I didn't put in this presentation. To me, they look like half ellipticals. They are kind of hard to describe the exact shape.
Sounds good. There was also a request, Casey, to put up the references slide. If you wouldn't mind, I'll transfer the powers back to you and we can put that up and see if anyone has any more questions. If there is something that we missed throughout this program, feel free to type it in again. I think I got all of them, but if for whatever reason I didn't, feel free to ask. We'll keep this open just for a little bit longer and then we'll conclude our presentation. Casey, I'll send it over to you right now.
Okay. Just need one moment to get it up there.
Sure, no problem. While you're getting up there, a question did come in. To be compatible with oar docks, the spacing of the hatches as well as their fore aft dimensions need to be consistent. Do you know when that was standardized?
Yeah, I can answer it unless you know, Casey. So it's
I'm sorry,
my understanding.
My audio cut out a little bit. I didn't hear the whole question.
Sorry, go ahead, Casey.
I'll restate it for you. To be compatible with oar docks, the spacing of the hatches as well as their fore aft dimensions need to be consistent. Do you know when that was standardized?
As far as I know, that was standardized in the early 1900s, I believe. I know with the 12-foot center standard spacing with the hatch covers. I know a major ship that was built with that standard design might have been the Augustus B. Woven that Kasey showed earlier, 1905. I believe that was when it became more standardized with all the different ore docks around the lakes. I could be wrong on that though, don't quote me on it, but I'm pretty sure that's when that standardization became regular on all different ships, and they're all standard today, as Richard has pointed out. So.
Excellent, thank you. There are no further questions. Kasey, if you could get that slide up, I don't think we're able to see it.
Yeah,
just
my
for Tom.
PowerPoint is just taking a moment to open up. Sorry about this,
Gotcha.
everybody.
Well, while we're waiting for her to get those references slides up, I'm going to conclude the program. If you'd like to stick around and see those, you're more than welcome to. Again, thank you everyone for joining us for the Virtual Visitor Center. We hope to see you again in 2 weeks. Stay safe and enjoy the rest of your week. Thank you.